Assalamu alaikum. Welcome to the next lecture. Uh, in the previous lectures, we discussed about the different controllers. We'll continue with the same. So, we're discussing about the controllers which are using the self-commutating switch. We discussed the shunt controller, that's STATCOM. Today, we'll discuss about the series controller, that is static synchronous series compensator. It is also shortly known as SSSC. It is a static synchronous generator operated without an external energy source as a series compensator whose output voltage is in quadrature with the controllable and independent of the line current for the purpose of increasing or decreasing the voltage drop across the line and hence thereby controlling the transmitted power. What it does, usually let us say this is the transmission line. This will be its receiving end, this will be its sending end. So voltage drop across this reactance, let us say it is Vx, and the current flowing through this line will be I. So this is its phasor diagram. This will be current I, this will be Vx. That's the voltage drop along this. Now what this triple SC does, it inserts a voltage source in series with this, such that if it is done in such a way so that Vx is in phase with this Vx, this V is in phase with Vx, so the total voltage drop across this will be, because now the line will be seen by the receiving end and the sending end as Vx plus V. So these voltage drop will increase the total voltage. V effective will be equal to V plus Vx. So in that case, Vf will be equal to V effective will be greater than Vx, this voltage, and we can say that as if this voltage source will act as an inductor, because you will see that this current will lag to this voltage by 90 degree. That means it will act as an inductor, and that's why it will the voltage drop will increase in this way. So when there is an inductive effect, total inductance will increase, the power transmitted will be decreased. Similarly, if it inserts a voltage source in other direction, so the total voltage drop will be equal to Vx minus V. You will see it will have a capacitive effect. So the total voltage drop will be now Vx minus V. Vf to be then less than Vx. It will have a capacitive effect. And total, since total impedance or total reactance will be decreased, power transmitted will be increased. So this is what a static synchronous series compensator can do. Usually, okay, we'll explain it a bit more. V effective is increased. It is as good as increasing the reactance of the line, thereby reducing the transmitted power and the fault current. This is usually used only in the fault conditions. V effective is reduced. It is as good as decreasing the reactance of the line, thereby increasing the power transfer capability of the line. This condition is met when this voltage is inserted in series, but it will be leading to this current by 90 degree. In this case, this voltage will be inserted in such a way so that voltage will be lagging to the line current, and this voltage has to be, since it is controlled by this converter itself, it will be independent of the magnitude of the voltage, as was not the case when we use the capacitors directly, because they will be dependent, their reactive power actually will be dependent upon the current flowing through them. If no energy source is required, we can only use a capacitor in the DC link. Capacitor is used in the DC link, otherwise no energy source are required. But if energy source is used also, we can feed some real power so that resistive loss can be compensated across the line. Not here like this, we have only a DC source. We can add here an energy source so that it supplies power to the line, which actually compensates for the resistive loss, because the power that will be sent from the receiving end to sending end, sending end to receiving end, there will be less power because of the loss in the transmission line. That power, if it has its own energy source, can be supplied by this, so that we can say that there is an energy exchange, real power exchange between these two. So this is the type of SSSC when it uses the voltage source converter. This is when it uses the current source converter. Now interline power flow converter. It is again a series controller. It is basically a combination of two or more SSCs which are coupled via a DC link. This is the DC link to allow the bidirectional flow of the real power between the AC terminals of the SSC. This is actually used to divert the power, because sometimes this may have more power. It will divert the power through this SSC to this line. If it is less power, it can take the power from this one. So it has a bidirectional flow of the real power. It can control the reactive power, and hence the real power can also be controlled. Reactive power can also be controlled here, and real power can also be controlled or exchanged. But the beauty of this is that the SC can be controlled to provide independent reactive power compensation for the adjustment of the real power flow in each line. So this is the prime motto of this. We want that there should be independent control of the real and reactive power. Now the combination of shunt and series controller, in this case we have a unified power flow converter, that is UPFC. It is again the combination of STATCOM and SSC which are coupled via common DC link to allow the bidirectional flow of the real power. Again, this is for the same purpose, but earlier case it was used between the two different lines, but this UPFC will be used for the same line. The real power flow will be bidirectional between the series terminals of the SSC and the shunt output terminals of the STATCOM, and they are controlled to provide both real and reactive power flow without any extra energy source. So you can see they are connected like this. This is the same line. This is the STATCOM and this is the SSSC. They are coordinated and they are linked through the DC link. We can control all the parameters, for example, voltage, impedance, and phase angle, and hence we can control the real and reactive power independently. In both the cases, we will be able to control the reactive and real power independently. But in SSSC, we have two different lines, and in case of this UPFC, sorry, in case of IPFC, we have two different lines, but in case of UPFC, we have the same line where we have to control the real and reactive power. And how these things are done, we'll discuss them when we actually study them in their respective chapters. For the time being, it was just the introduction of different controllers that we are going to study in this subject. Let us now come to SVC. And the part of the SVC we'll discuss first the TCR, that is thyristor control reactor. Basically, thyristors, as we have seen, they are not used individually. They are used along with a fixed capacitor or TSC, that is thyristor switched capacitor. So it becomes TCR plus fixed capacitor or TCR plus TSC. By controlling the reactance, we can control the whole impedance. Reactance of this, we can actually control the whole impedance of the SVC. So first we'll discuss TCR, and after that we'll see what will happen to the this SVC. Let us say this is the actual line, actually the second row of the converter transformer, and the voltage across this is Vs. This is thyristor 1, this is thyristor 2. So this is the current flowing through this, that is ITCR, that is flowing through this, and we know that the control range of firing angle for this case will be equal to pi by 2, from pi by 2 to pi. And let us say sigma is the conduction period. This is the period in which current flows in this circuit. This is Vs, and we know that alpha has to be greater than 90 degree to have a proper control. Let us say it is greater than 90 degree and alpha is alpha greater than 90 degree. That means let us say it is for TH1, and it is TH1 will conduct. TH1 when conduct, we have the output voltage. This will be the, this is Vs, output voltage will be this, because it will conduct at that point. Now current will start flowing in the circuit. Current will start flowing in such a way so that the average voltage across this inductor will be 0. That means from here to here, the current will be 0 at the point when this voltage, that is the voltage from here to here, will be same as the voltage from here to here. The total voltage area from here to will be equal to here, so that net voltage or average voltage between them will be equal to 0. So this is the current pulse in we can say for this thyristor, and then a TH2 will be triggered at alpha is equal to greater than 90 degrees. Alpha will be measured with respect to this point, and this will be its alpha, which will be greater than 90 degree, and it will be equal to this alpha with respect to 0. So the voltage for this case will be equal to this much from this, and the current will go until this average voltage comes out to be 0. It will be this. So when we draw the fundamental, you will see that it is symmetric. It is fundamental will be drawn like this. This is the fundamental component of the current, source current, and it lags the voltage, uh, source voltage by 90 degrees, and it has to be there because this inductor is of inductive nature. It draws the current which lags to its voltage by 90 degrees. So this is also with uh, as per the general rule. So here phi will be equal to 90 degrees. Actually, should have phi 1, that is the power factor angle, or we can say phase angle of current, but it should be the fundamental component of the current. It is inductive current. So we can say that current is lagging to the voltage by 90 degrees. So the conduction angle will be from this to this. You can see from here. Okay, that will be there. Let us discuss only this much. We'll see other things after this. So let Vs is equal to Vm sine of omega t, and during conduction we know that Vs will be directly applied to the inductor, so it will be equal to L di by dt. So Vm sine of omega t, because Vs is equal to this, will be equal to L di by dt. So let us multiply and divide by omega on both sides. It will be omega L di by d omega t. Because we are actually integrating, our time domain is not t, it will be omega t. So then I will be equal to this, I will be equal to, will take this d omega t to this side, will be equal to integral of 1 by omega L Vm sine of omega t will be equal to I. So Vm by omega L, and we will integrate from alpha to omega t. Omega t is an arbitrary time in the conduction angle. So omega L, when we integrate it, it will be equal to minus cos of omega t. I will write it as it is without limit. Even if I write the limit directly, I can get the same answer, but I want you to first try to do it without limit. After doing it with limit, it will be same. So its integration will be minus cos of omega t. So I is equal to Vm by omega L minus cos of omega t plus C. At omega t is equal to alpha, you can see from here. At omega t is equal to alpha, this I is equal to 0. When this is equal to 0, that means this is 0, Vm by omega L minus cos of alpha, omega t is equal to alpha plus C. C is equal to Vm by omega L cos of alpha. So putting the value of C, I of t is equal to Vm xl, where xl is equal to omega L cos of alpha minus cos of omega t. This is the expression of the current from this point to this point. Since firing angle ranges from 90 to 180 degree, it will be convenient to measure the alpha from 90 degree. That means we are making this origin, or alpha is measured with respect to peak of the input voltage instead of with respect to zero of an input voltage. In that case, it will be slightly convenient. So this will be our origin. Now alpha will not be this much, alpha will be only this much. Let us call it for the time being only alpha dash. So rest will be same. Only thing we need to measure alpha with respect to peak. So in that case, the origin is now the peak of the input voltage. Current, actually current is full of harmonics. Because of the odd symmetry, even harmonics will be absent. When we take this as the origin, you will say current has the odd symmetry. When current has the odd symmetry, the component of the harmonic series or harmonic components, or we can say uh, Fourier components of an will be 0, bn will be there. So we need to find out only fundamental component of the current, that b1 will be equal to 2 by pi from 0 to pi I of omega t sine of omega t d omega t. So first I will try to convert this virus. Just a minute. I don't know where. Just a minute. Okay. Now from here, please. I have missed that slide over here, but I will explain it. Let us call this as alpha dash. This alpha, not alpha, it will be alpha dash. This alpha dash will first find a relationship between this alpha dash and this alpha. the actual alpha, which already we have discussed, which is measured with respect to this. Alpha dash will be equal to alpha will be equal to 90 plus alpha dash, because this will be alpha dash, total alpha is this, that means this 90 plus this alpha dash will be equal to alpha. And similarly, if we measure this omega t dash with respect to this peak, so omega t dash will be nothing but uh, the time that is measured with respect to the peak of this omega t dash from here to here plus 90 will be equal to omega t. So replacing alpha by alpha dash plus 90 degrees and omega dash omega t by omega t dash plus 90 degrees, you will see that this will be now cos of alpha dash plus 90 degrees. It will be equal to minus sine alpha. Similarly, cos of omega t dash plus 90 degrees, it will be equal to plus sine of omega t dash. So that is what I have written over here. And then without referring again, uh, I always take this omega t dash is equal to omega t and alpha dash is equal to alpha, but keeping in mind that these are with respect to the peak of input voltage, and this is the case. So then this it, that's I omega t, will be equal to sine of omega t minus sine of alpha. So v1 is equal to 2 pi pi 0 to pi I of omega t sine of omega t dt. I omega t has to be replaced over here, that will be v by xl. This will be equal to minus sine of alpha plus sine of omega t. Actually it should have been minus sine of alpha dash plus sine of omega t dash. Since I replaced alpha dash by alpha and omega t dash by omega t, but we have to keep in mind that alpha is now with respect to peak and omega t is now with respect to peak of the input voltage. So our equation for I of omega t becomes sine of omega t minus sine of alpha. This sine of omega t is from this, so it comes out to be like this. Then this will be twice Vm by pi x of L. This is from the formula, and our current is there from alpha to pi minus alpha. You can see from here, this is alpha. This also will be alpha because of the symmetry. So current will be from this to this is pi. This is alpha. That means from alpha to pi minus alpha. So multiplying this sine with this sine to be sine square omega t minus sine alpha into sine of omega t, it will be equal to this value. So splitting it in the in this form, to be equal to 1 minus cos of 2 omega t divided by 2, it is as it is. So this will be 1 by 2 minus cos 2 omega 2 by 2 minus sine alpha sine omega t d omega t. So when we integrate it, it will be equal to omega t, and given the value, it will be pi minus alpha, that is this. So I have integrated it, it will be equal to sine of 2 omega t divided by 2, and it has its own 2, it will be 2 into 2 will be 4, and it has to be integrated from now. There will be limits are to be given for alpha and pi minus alpha. Similarly, for this case, to be equal to sine of alpha cos of omega t. So actually it should have been minus cos of alpha, and upper limit should have been pi minus alpha and lower limit should have been alpha. So I have consumed the minus in the limits. I have written the upper limit to be lower limit and lower limit to be the upper limit, and then this minus will be consumed automatically. So this will be equal to pi minus 2 alpha. This will be sine 2 pi minus 2 alpha. This will be sine 2 alpha. For this case, divided by 4. This will be cos of alpha minus cos of pi minus alpha. Cos of alpha minus cos of pi. Now this will be sine of 2 pi minus sine of sine of 2 pi minus 2 alpha. It will be equal to minus sine 2 alpha. Sine of pi minus alpha. That means in the second quadrant, cos will be minus. It will be then plus cos of alpha. So total quantity, it will be pi minus 2 alpha by 2 minus minus sine 2 alpha minus sine 2 alpha divided by 4. It will be minus sine alpha. It will be equal to cos alpha plus cos alpha. So this will be equal to minus twice sine alpha by 4. That will be equal to minus sine 2 alpha by 4. But minus and minus will be plus. It will be sine 2 alpha by 2. And this is minus. It will be equal to sine alpha into twice cos alpha. So pi minus 2 alpha by 2 as it is. It will be sine 2 alpha by 2 as it is. It will be sine 2 alpha twice sine alpha cos alpha sine 2 alpha. So it will be 1 by 2 minus 1. It will be minus 1 by 2. here, because sine 2 alpha will be taken as common. It will be 1 by 2 minus 1, it will be minus 1 by 2, it will be sine 2 alpha by 2. Now multiplying by 2 by pi, you will see this 2, and this 2 will cancel out, and then when you divide by pi and pi will be, pi divided by pi will be 1. This will be 2 alpha by pi minus 2 alpha by pi, and 1 by pi sine of 2 alpha. So this comes out to be the value of B1. That is the peak of the current, fundamental current. So peak of the fundamental current as a can say function of alpha will be this Vm by xl 1 minus 2 alpha by pi minus 1 by pi sine of 2 alpha. So V is equal to Ix, we know that. This is the equation, or I is equal to V by X, or V into B, where B is the 1 by X, that is the of susceptance of the any circuit. This is actually for the general purpose. Similarly, I can write it as I1 alpha is equal to Vm into BTCR alpha. I am actually writing this equation now in terms of this equation, where BTCR alpha will be this term. So whatever be there is multiplication with Vm, that will be simply susceptance, and that susceptance will be 1 by XL 1 minus 2 alpha by pi minus 1 by pi cos of 2 alpha. This is very important result. So I can write it as BTCR max or B max 1 minus 2 alpha by pi minus 1 by pi sine of 2 alpha, where BTCR max or B max will be equal to 1 by XL. You can see from here, when alpha is equal to 0, now alpha is with respect to pi. So with respect to this pi by 2 or peak of input voltage. Now when alpha is equal to 0, this is 0, this is 0, it will be equal to BTCR max, that is equal to 1 by XL. So in that case, maximum current will flow through the circuit, or there will be minimum reactance in the provided by the this, what is its name, BTCR, this TCR. When alpha is equal to pi by 2, and this is pi by 2, this will be 1. This is 2 by pi into pi by 2, 1 minus 1 is 0, and this is pi by 2, 2 and 2 will cancel, sine pi is 0, this will be 0. That means BTCR alpha will be 0, there will be no current flowing through the, or we can say it is offering infinite reactance, it is an open circuit. So for the time being, I think this is enough for today. We'll continue in the next class. Thank you.